Recording in progress.
Okay, welcome back, guys. Sorry I had a little bit of delay, but we're back online. All right, couple of things. I am still having challenges with Canvas. And anyway, so not everything has been great. But I hope everyone is at least got back online and not having a problem getting to their course. I did send an email. I had to do this for legal things about the syllabus. Hopefully you got it. If you didn't get it, let me know. It could have been a Canvas thing again, but I just basically all it is, same syllabus. I just moved the dates forward. So we all know that everything's been moved forward ahead. Now there's also one assignment, I believe it was due yesterday. Chapter 10, we have not done chapter 10, and as I stated in the past, it won't be due, any assignment won't be due until we're done with the chapter. So I moved it till tomorrow, no, day after tomorrow, I forget which one, but I moved it. So not to worry. Now, if you took that assignment and did it already, but you want to do it again, and you did it before we got completed, let me know. I'll give you another attempt on it. All right. Hope everybody's doing okay. Everybody's doing safe, being safe. Let me share the page that we ended up with. And this is where we ended up. We were talking about double displacement reactions. This is the chapter in the 6 types of different reactions, okay? And this one here deals with 2 reactants that are soluble in a aqueous solution. So you'll always see that the reactants are soluble, and you'll see the AQ notation, okay? And so that tells me I got 2 soluble reactants. They haven't been put together yet. They will be put together, and then a process may occur or may not occur. If one of the reactants is insoluble based on the solubility rules found on the periodic table, then you get a positive reaction, okay? If the new products you obtain are both soluble, okay, then there's no reaction. Okay, so let me restate that again so we're perfectly clear. The 2 reactants that you get are both soluble. After you exchange partners, because this is basically what happens, you get a new set of products, and basically the cation of one exchanges with the anion of the other. And we'll go through that here in a second. Then you look at the solubility of the new products. If both of them are soluble, both of them are soluble based on the solubility rules, then there's no reaction. If one of them, or even both of them, are insoluble, then you got a positive reaction, okay? All right, so for these type of reactions, what we want to do first to find out the new products is to first write them down in ionic form, okay? And so what's happening here? The lead is going to exchange with the iodine, okay? And I'll change a different color. The nitrates are now going to combine with the potassium. And so I'm going to write the new products in ionic form. Now, why I do this is because I want to make sure that I put them together with the proper number of cations and anions such that they cancel each other out, and I get them in the right ratio together. So the new products, I'm going to go back to red, will be the lead. Now, question is, which lead do we have? Because this lead, we don't know for sure if it's, what's its oxidation number, okay? Remember, it's one of those variable oxidation numbers. So we need to calculate, we need to figure it out. If you look at the nitrates, NO3, you go to the polyatomic ion table, you'll find that the nitrates each have a -1 charge, okay? And since I have a -1 charge for the nitrates, that means I got 2 negatives for the nitrates, which tells you that I must be working with lead Roman numeral 2. Okay. Now the partner for the the new partner is going to be the iodide. Well, we know that iodine is in group 7. We know when it's going to become an ion, becomes ionic, I should say, it will have a -1 charge because it picks up 1 electron. It's in group 7, now has 8. So the new partner system is between the lead and the iodide. I'm going to need 2 iodides for each lead to cancel out the positive. So the formula for the new product will be lead IQ. Okay. Now let's figure out the one for the other product, which is potassium. We know that potassium is a group 1 and therefore will always have a +1 charge. We just talked about the nitrates. The nitrates are -1 charge, but finding them on the polyatomic ions, they got a -1 charge. So now I can combine the two in a simple 1-to-1 relationship. I don't need parentheses for the nitrates because I just need 1. And so my other product will be potassium and O3. So those are my new products, okay? Now, before I even go any further, I want to check to see if any one of these are what the solubility status is. Well, the fact that I got potassium right out the top, up front with potassium nitrate. Now remember, I'm just looking at the fact that I got potassium, I don't need to go any further. Why? Because in the solubility column, the big 4, as I call them, you got potassium. Whatever potassium is bonded to will always be soluble. So it's AQ because we're in the aqueous system. All right, so that takes care of potassium, which brings us back to the other one, the lead 2 iodide. Well, we know we find the iodides on the table, and normally the iodides, specifically here the halogens, in this case chlorine, bromine, iodide, are soluble. Normally they're soluble, except when they're bonded with the big metal, the heavy metals, okay, which lead happens to be one of them. And so this tells me that lead iodide is insoluble, therefore I have a positive reaction. Okay, so first step, write the ion. Second step, write the new formulas correctly, making sure you got the right numbers of cations and anions for the new formulas. Second step, look at the solubility rules for the new products, determine whether they're soluble or insoluble. Any one of these products is insoluble, you have a positive reaction. So now you got to go through the third step. And so the third step is to balance it. And to balance the reaction, my suggestion is this: follow the polyatomic ions. You're going to find 9 times out of 10, these type of reactions, you have polyatomic ions, okay? So look at the nitrates. Nitrates, I got 2 nitrates as reactants. Well, I need to balance those nitrates. So what I do is I simply put a 2 in front of potassium nitrate. What that does is it balances out my nitrates. I got 2 as products, 2 as reactants. In the process of doing that, that kicks up my count for potassium. Now I got 2 potassiums. Well, then I go back to the reactant side and I put a 2 in front of potassium iodide. What that does now is kicks up my potassium count to where it's balanced. Notice how we're going back and forth, back and forth. So now my iodides have increased, okay? So now I got to check those. And I go back to the reactant side for my iodides, and lo and behold, by default, they get balanced because I needed 2 of them to begin with. And it just falls into place there. So now I go back and double check everything. I got 1 lead as a reactant, 1 lead as a product. I got 2 nitrates as reactant, 2 nitrates as product. Okay, those are good. I have 2 potassiums as product, and 2 iodides and 2 iodides as product. Therefore, I have a balanced chemical equation. So let me clear my mess, and we'll bring in the more ordered material. And here we are. And so my step was first, as I stated, write the new products in ionic form. So you can write them correct in the right formula. Check the solubility. If any of the products are insoluble, you got to react it. If they were soluble, then you have no reaction. And you were right, and R for no reaction. Okay. All right. Let's do another one. One more. Okay. Like anything, the more you do it, the better, the more confident you get in this. All right. So now we have the reaction of barium chloride, aqueous, obviously, plus a silver nitrate, also aqueous. So both of these are clear solutions. I have them in the beaker, and then something's going to happen when I mix them together. Well, go through the same format we just did. First thing to do is to determine the new products. Again, we're going to combine the barium with the nitrates, okay? And we're going to combine the silver with the chloride. Those are our new products. So first thing we do is write everything in ionic form. Now, barium, we know that barium that has a +2. Two reasons why we know we have two ways to determine that. One is obviously barium's in group 2. It's ionic, so it will lose 2 valence electrons. I end up with a +2. But if you forgot that, you also should know that chlorides each have a -1. They're halogens. In ionic form, all halogens have a -1. Since I have 2 of them, that implies that barium must be a +2. Okay, so that verifies it. The nitrates, well, we know about the nitrates because they're in the polyatomic ion table. We also talked about them in the last example. We know that I put a circle over my charges just for me, so I know that those are my charge. So I know that the nitrates each are -1. Now, to get the barium and the nitrate combined, I need 2 nitrates for each barium, which tells me that I'm going to need parentheses around the nitrate. So I can go ahead and write the new formula for barium nitrate. And that's as follows, okay? Now, for the other product, I'm going to go back to the color. Silver, we know, is part of the sweet 16. Remember those 16 elements that we knew that always have a constant oxidation number? Silver always has a +1. The chlorides, we talked about that. Halogens will always have a -1. Therefore, I can combine the two in a simple 1-to-1, and my new formula will be silver chloride, okay? Okay, next step, figure out the solubility. Let's look at barium nitrate. Well, we can go directly to the nitrates, which is on number 3 in the solubility table. And what that tells you is this: whatever cation is bonded to the nitrates, always soluble, okay? Regardless of what the cation is. In this case, we got barium, doesn't make any difference. It is always soluble. So barium nitrate is soluble in water, aqueous, okay? With respect to silver chloride, okay, we go to the halides, number 4 on the solubility table, and we see chloride right there. Normally, all the chlorides are soluble, normally. However, when it is bonded to the big three heavy metals, which happen to be poisonous and bad for your health, silver ion, mercury ion, and lead ion, when they are bonded to them, they are insoluble. Therefore, we have silver chloride as an S or a solid because it's insoluble, which then tells us we have a positive reaction, okay? Positive reaction. So now that we go to the next step and we balance it. Again, My suggestion here is to follow the polyatomic ions. Okay, and you can see here that on the left side of the reaction, we have one nitrate, but on the right side, as products, we have two nitrates. So we all simply got to do is put a 2 in front of silver nitrate. Okay, well, then that kicks up my silver count. Okay, balances my nitrates, but my silver goes up, no problem. We go down to the product side, put a 2 in front of silver chloride, and that balances my silver. Well, as always, when we do that, something goes up. In this case, the chlorides go up. So now we're going to go check the chlorides, and we see that the chlorides are already balanced because of the nature of barium chloride, which is a +2. So we got 2 chlorides. So now we have a balanced chemical reaction. We double check, we got 1 barium reactant side, 1 barium product side. We have 2 chlorides reactant side, 2 chlorides reactant side. Okay, we got 2 silvers, we got 2 silvers product side, 2 nitrates reactant side, 2 nitrates product side. Okay, our states are all there, and we have a balanced chemical equation. So now we can clear it and bring down the ones that are better written than my chicken scratch here. My pad is not the best resolution. Okay. And so we have 2 barium chloride, 2 nitrates, silver nitrates, and 2 barium to give us 2 barium nitrates aqueous and 2 silver chloride solids. And that is our chemical reaction. So we got a positive reaction. Again, we got a positive reaction because one of the products of this double replacement reaction was insoluble. Now, with respect to this term called redox reactions, okay? The term redox is a combination of 2 words, oxidation and reduction. Okay. And it's simply put as this. If let's say whatever reactant, let's say element A, if for some reason this process is a metal and it loses an electron, okay, it ends up with a positive charge because it lost an electron, right? Here's our electron, negative right here, okay? We call that oxidation. The name for loss of an electron is called oxidation. One way to remember X for electrons exit the building, so to speak. Maybe that helps. So when you lose electrons, you undergo a process called oxidation. Now, when, let's call this B, keep it separate. When an element or a compound gains an electron, okay, in this scenario, now it has an extra electron, it has a negative charge overall. We call that reduction. Okay, so one way to remember that, if you want, is the electron returns to you. Who knows? Maybe that helps. So learn one, the other one's the opposite. So oxidation is simply the loss of electrons, and a reduction is the gain of electrons. And so by combining letters from those 2 words, you end up with the term called redox. So a redox reaction is a process where it occurs simultaneously. It doesn't occur separately. You cannot lose an electron without something else picking up the electron. It occurs simultaneously. Now, many of these reactions that we just talked about, single replacement, combination, decomposition, combustion reactions, are also known in the generic term as redox reactions because there are loss of electrons and gaining of electrons that are occurring. Right now, as we speak, if you're operating your electronic device on your battery or your cell phone right now, whatever you're using as a battery, you have a redox reaction occurring because on the poles of that battery, on one side, electrons are being lost, and the other side, electrons are being gained. Okay, and you're tapping into the gain of electrons that occurs spontaneously in a battery, and then the instrument, the equipment, electronic equipment utilizes the electrons that are being generated to operate properly. And then when you run low on batteries, you come back, plug it in, and what that does, it reverses the process, kind of bring everything back up to the top of the hill, if you will, with respect to electrons. And then when you take it off the charger and you start using, you're going down the hill because it's a spontaneous process of this electron movement. Eventually the batteries go bad because they can only do that so many times of reusing and recharging. It starts to break down and you got to replace the battery. All right. So there's nothing magical about that battery, just electrons. Okay. So redox is short for the term reduction and oxidation. Reduction is, like I said, something, and when you gain electrons, your element charge, your oxidation number goes down in value, right? Because if you're at 0 oxidation number and you gain an electron, now you go from 0 to a -1. Your oxidation number value went down, okay, to a negative value. If you lose electrons, guess what? Your oxidation value goes up, becomes a positive number, okay? And they're trying to explain to you in those terms. Oxidation is when element charge goes up, okay? So you might say, well, I don't understand yet. Okay, well, think of it as a graph, okay? Just like we got 0 right here. And as we go up the graph, you go, +1, +2, +3, and you go down here, you go -1, -2, etc. So you start off at 0, you lose an electron, now your oxidation number goes 2 + 1, so your oxidation number goes up. If you start at 0 and you gain an electron, well, now your oxidation number goes to negative, and that value goes below 0, so your oxidation charge goes down, okay? That's what they're trying to use it as an analogy. Okay, and the thing to remember also is a redox reaction occurs spontaneously. You can't have one without the other. One goes reduction, one goes oxidation. Review your oxidation numbers, okay? Remember what we talked about. We know that elements in their natural state, all 118 elements have an oxidation number / charge of 0. Why is that? Because it has an equal number of protons, which have a plus charge, and an equal number of electrons, which have a negative charge. So our net is 0. When these elements start to lose electrons or gain electrons, that is when the oxidation number changes, because it's either going up or going down, because you're either losing electrons or gaining electrons. Okay, and those are the ions. Remember, ions. All right, so recall group 1, group 1A, all those metals in there, and including hydrogen, will lose an electron, end up with a +1. Group 2 end up with a +2. Group 3 end up with a +3. They lose electrons, okay? It is where you get to group 4. Group 4 can be thought as being on the fence, where depending on the reaction conditions, you may either lose. Group 4 has 4 valence electrons. So it could lose 4 electrons, or on the same token, it can gain 4 electrons. Remember, it's the driving forces to get to the octet. So you can have an oxidation number from a -4 to a +4, quite a range if you're in group 4. After group 4, you're gaining electrons, okay? So group 5, you're gonna pick up 3 electrons, give you a total -3. Group 6, you're gonna have a total of 2 electrons, -2, and group 7, a -1. Okay, so you refresh your memory on those. And as we know, group 8 are the noble gases. Noble gases, that's it. They're not going to react, okay, because they have 8 valence electrons. They have fulfilled the infamous happy 8, the 8 valence electrons, except helium, who has the infamous duet rule, 2 electrons, okay? All right, so refresh your memory in that. Then we talked about the charges that we know, group 1, group 2, always +1, +2. There's a total of 6 electrons, elements there. That's a total of 6 from group 1, 6 from group 2. That's 12. Then we talked about silver always has a +1. Zinc and cadmium always have a +2. And the one that's missing here is aluminum as a +3. So that's the 16 that you know its oxidation state 100% of the time. There's no variation there. All right. So to better understand, hopefully, oxidation is losing electrons and the charge goes up, okay? And that example is here. We have copper metal, which has a 0 charge. Remember, it has a 0 charge. Now, the moment it loses 2 electrons, and now has a +2 charge. And so its oxidation number went from a 0 to a +2, went up, okay? So what we say here, that solid copper is oxidized. Now, because redox reactions occur simultaneously, those electrons are just not going to hang out there someplace. Some other species is going to pick those electrons up and they're going to undergo reduction, okay? Therefore, what is being oxidized is also named as the reducing agent, because it supplied the electrons that somebody else or something else is going to pick up, to undergo reduction, okay? So what is oxidized is called the reducing agent, and the oxidation number goes up when you lose electrons. All right, so take, for example, sulfur. Gaining of electrons, the charge goes down. So here we have, again, another example where we have sulfur, which has an oxidation number of 0. It's the element, no charge, right? Well, it picks up 2 electrons because it's in group 6. So it wants 2 electrons because it fulfills the octet by picking up 2 electrons. And now it's become isoelectronic with argon, the noble gas in front of it, okay? And in the process, now it has a -2 charge. So it went from a 0 to a -2 charge. And therefore, its oxidation number dropped, went down. Sulfur is reduced, which now makes it the oxidizing agent. So what is reduced is called the oxidizing agent, because it is utilizing the electrons that another element gave up to undergo reduction. So now it is classified or named as the oxidizing agent. Okay. So as we just stated, you can't have one or the other. And so what is oxidized and what is reduced is always the reactants. The products here have nothing to do with anything. It's always the reactants. Those are the guys that undergo oxidation or reduction, okay? So what is oxidized and what is reduced, if you're asking the question, is which one of the reactants is undergoing oxidation or reduction. And once you determine that, it is the whole compound. It could be an ion, but it could be a whole compound, like copper chloride can undergo reduction to copper metal. We'll have an example here in a second. All right, so for example here, let's break this down. We have 2 reactants here. We have copper +2 because we got a plus charge. Now, you might ask, wow, would this reaction even occur? I'll tell you what, to go to the activity series, okay? And you will find that iron is more reactive than copper from the activity series. And then remember the second question we would say, ask, we'll say, is the most reactive metal in ionic form? Well, no, it's in elemental form, so reaction proceeds. So yes, this reaction will proceed, okay? Normally you will see it with the corresponding anions for the copper, but right now they're just showing you the cation. So copper 2 goes from a +2 state to, guess what? A 0 state, okay? Now think about it. If I got a +2 number, how can I make it into a 0? Well, I add 2 electrons, do I not? Because if I add 2 electrons, I cancel the +2 charge, and now I got a 0 charge. Another way of saying, if I got $2 in my pocket and I spend it, I buy something for $2, what do I got left? 0, okay? Same thing here. So here we go. We got a +2 goes 0. Going from a +2 to 0 is gain of electrons. So copper 2 ion is undergoing reduction. Well, because its oxidation number is going down, isn't that? Okay. Now, if we look at iron, iron starts off as 0 and it goes to the +2 state. And so that means that iron underwent oxidation. Okay, because it gained electrons. All right, so let me clear this up. And so here we got copper 2 going to 0. So the charges went down, so it underwent reduction. Okay. And then iron went from 0 to +2. So the charge went up, so it underwent oxidation. And so what is oxidized is iron, and what is reduced is the copper 2 ion, which means that the copper 2 ion is the oxidizing agent and the iron is the reducing agent. Okay. All right, here's another example. This actually is a real example. It's utilized, one of the compounds that is made is utilizing cancer treatment, platinum compound. All right, so we have cobalt 3 nitrate reacting with platinum to give us platinum 3 nitrate and cobalt. Okay, so the first thing we look at, we see that cobalt goes from what to what? We go from a +3 to 0, right? How do we know it's a +3? Well, we know that the nitrates each have each nitrate has a -1 charge. There's 3 of them, so there must be a total -3 here that tells you that cobalt must be a +3 charge. And it goes from a +3 to 0 because this is an element, okay? This is an example of a single replacement reaction, okay? Excuse me. Don't have platinum on there. Okay, now if we look at platinum, platinum starts off with a 0 because it's an elemental form, and it goes to platinum 3. Okay, how do we know it's platinum 3? Because again, like we did with cobalt, we know the nitrates are each -1, and there's 3 of them, so therefore that is a +3 state for platinum. So, excuse me, what is oxidized is the platinum. Platinum is oxidized because it lost 3 electrons in the process. And what is reduced is not just the cobalt itself, but it is the whole species, cobalt 3 nitrate, okay? And so therefore, that is also the oxidizing agent, which makes platinum the reducing agent. Okay. All right, yeah, that platinum platinum compound is used quite a bit in treatment of cancer. It does something very specific. Very interesting reading. All right, well, we know the name for cobalt nitrate, cobalt-3 nitrate. We went through that explanation. We know the nitrates each are -1. We know that cobalt is not part of the 16, so we got to use Roman numerals. So therefore, 3 nitrates at a -1 tells us that must be cobalt-3 nitrate. Okay, so this is oxidation reduction. Dr. Kim, more YouTube videos on there for you to watch and listen to Dr. Kim's her version of presenting this chapter. The more ways you hear the topic, maybe the better understanding of it you have. So helps you out. So summarize here for this particular chapter. Be familiar with the solubility rules. You know how to use the solubility rules. You don't have to memorize them because you got the periodic table, but be familiar how to use that table. Okay, we went through it a couple of times now. Also, same is true with the activity series because you need those to answer some of the questions if you're asked. Okay, be able to recognize and balance combination reactions. Combination reactions normally entails the two elements coming together to form a compound. Hydrogen gas plus oxygen gas combine to form water, H2O. So normally two elements coming together to form a compound. And the opposite again, you have a compound that something's done to it where it breaks it back down to the elements. So water is another perfect example. Water can undergo electrolysis. You hit it with some electrical current, you break up the molecule of H2O, and you regenerate the hydrogen and the oxygen that was used to make water. That is a decomposition reaction. Recognize, write the products, and balance single replacement reactions, okay? And that is normally where you have a element metal reacting with an ionic element compound. And so what you do, use the activity series here to determine which metal is more reactive. And if the most reactive metal is already in ionic form, then there's no reaction, okay? If it's not, then there is a reaction that proceeds, okay? I also talk about balancing them out. Double replacement reaction, this is where you form a precipitate if you have a positive reaction. Here you utilize the solubility rules, okay? We did an example of that one earlier. Acid-base neutralization, well, we had a whole chapter on acids and bases, but basically remember that when you have a proton, which is the acid part, and a hydroxide, okay, combine to form H2O. So the acid proton and the base hydroxide are neutralized to give you water, hence the acid-base reaction. To balance this, follow the hydroxides and the protons, okay? If you have two hydroxides on one end, you're going to need two protons, okay? So that helps you out. Follow that, which is going to give you two waters, and then the rest of them fall into place. The combination, decomposition, and single replacement, normally pretty straightforward. They're not as complicated. You can use a trial and error method. Double replacement reaction, to balance those, follow the polyatomic ions. Those normally are 99 times out of 10, they have polyatomic ions in there. Follow the polyatomic ions to balance that equation. And the acid base here, follow the protons and the hydroxide. All right. And so then we have a combustion reaction. Now, combustion reaction, two things that come into mind. One, you're always, for Chem 130, the only thing you're going to combust are hydrocarbons. Those are species of compounds that have nothing but carbon and hydrogen. X and Y may vary, okay? Now, obviously, you know well enough that for combustion, for anything to burn, you need oxygen. So oxygen will always be a reactant. Plus, you know that oxygen is a gas, okay? And the only products that you're going to get at M130 with respect to combustion of hydrocarbons is water and carbon dioxide, okay? That's it. All right. Yes, I understand you can get carbon monoxide, but we're talking ideal conditions here. I mean, I'll get the two mixed up here. All right. Now, to balance combustion reactions, we had a stepwise method, right? We had first balance the carbons, second balance the hydrogens, and third finally balance the oxygens. All right. Clear that up. And then, like we just talked about, what is oxidized, look at a reaction, be able to identify what is being oxidized, what is being reduced, and then the corresponding agents for a redox reaction, okay? All right, folks, with that being said, congratulations. 5 more chapters to go. And the next chapter, believe me, is extremely short, 11 pages. Okay, anybody have any questions about this? I'm going to jump into the next chapter, which only has 11 slides, and we'll get done. We'll get done with that today. We'll be a little bit early. All right. Any questions, comments? All right, I don't know if you saw my background here. There's the metric system prefixes, FYI. Very need to use them. I don't know if you can see them or not. Let me get out of the way. There you go. Okay, next chapter, chapter 11. Now, we've been talking about reactions here, and we've already introduced to you these 6 types of reactions. But the thing about these reactions is all reactions, they're related to this area of chemistry called physics/chemistry, called thermodynamics. Now, very complicated word, right? But to break it down, you know, I'm always about breaking what you see, these words, and breaking them down. You find out they're not as complicated as you think. Okay. We got the word thermal. Thermal makes, you know, we're talking about heat energy. That's some kind of relationship. And then we're talking about the dynamics, maybe the movement of things, how things interact with each other. And so maybe you can deduce that thermodynamics has something to do with heat, energy, and how things move relative to that. And what we're going to talk about is simply the tip of the iceberg pertaining to thermodynamics, because all reactions are about 2 things really. When you boil it down, you bring it down to it, is one is stability, whether the products you make are stable, because even though the product looks like something you can make, it may not be stable in that normal, in say room temperature. It may break down further to something else. And that's been a challenge at times in making compounds, is trying to find ways to stop it in the state that you want it. But because it's so unstable there, it's going to break down to something else, because Mother Nature always wants to be in the most stable state that it can be. So stability is a big factor. The other factor is this. If you think about it, if you play the numbers, let's say you're in the room you're in right now, you represent a reaction vessel, and I have, you know, you might be in a bedroom or big house or whatever, and your house or your big room represents a reaction vessel, and you got 2 tennis balls. Okay, one is a blue one, one's a yellow one. Okay, now the idea is these 2 tennis balls represent reactants A and B that come together. It's a combination reaction to form this compound. Okay, well, think about it. If I'm in this big container and I got these tennis balls that I wanted to come together to form that product, if I only got 2 of them in this big giant room, the probability of those guys coming together to create a product is pretty low. So concentration is a big factor to get a product. And a lot of times what we got to do, we got to up the concentration to assure that these two reactants come together. Another thing, we know that molecules do not move. Compounds, I should remember restate that, move, okay? They're not just sitting there. They're moving around depending on the physical state that they're in, especially in the gas stage, they are moving around. So one way I can do to get these guys to come together is maybe fire them up a little bit, get a little energy into them, heat them up. That increases the probability that these two balls that I talked about, tennis balls, come together because they start moving around, okay? And increase the probability of coming together. So concentration is a factor. The other thing is maybe I got to heat them up like I stated. But once I do that, if they don't come together with the right orientation, nothing's going to happen. The biggest example I could show you or demonstrate is if you shoot pool. I don't know if you shoot pool. Back in the day, man, I was a little bit of a shark, but pool shark. Not anymore. But in the day, you could take the cue ball. If you're not familiar with shooting pool, billiards is another term for it. Yeah. So you got a pocket and you got the cue ball and you're trying to make a ball into the corner pocket. Well, you got to hit that ball, the cue ball, with the right amount of energy, not too hard, not too fast, the right amount of angle so you can angle it off depending on how you start off, angle it off to the side pocket. Okay, so you have all these variables in there. And those are chemical reactions. If you don't have all those variables just right, you're not going to get the right product to make. So it's a little more complicated than just put an A and B together and, do some Harry Potter stuff and voila, and there it is. Reaction kinetics is the field I worked in for a long time as a graduate student. Takes a lot of work and you gain a lot of information. Okay, so what we have here is what we call collision theory. Okay, molecules got to hit, collide in order to react and to make a product. So if we look at this particular diagram, you can see we have two diatomic reactants, obviously a different color here, so you can see they're different. They're both diatomic, and the goal is to, let me change the color here a little bit. That red, doesn't come out too good. The goal is to get the reactants to come together to create two different products, right? Okay, and so what's happening here is we're breaking this bond between the two light color diatomic molecules, and we are creating a new bond. Okay, and so you can see the orientation has to be just right, and we get this intermediate where we're getting it's like a hybrid of the reactant, a hybrid of the product. It's like the metalloids have properties of reactant, properties of product, where we're getting some bond breakage going on here and some bond formation going on here to create the two products. That spot that has a little bracket around it is called the transition state. It occurs very quickly. It's getting from point A to point B, okay? But it needs to get through this center area called the transition state. Now, it requires the right amount of energy to get to that state and the correct amount, the correct orientation to get to that state. If that orientation isn't like it's written, then we're not going to be able to bond break and so forth, okay? You will create new bonds to make the new product. So there's a lot of stuff going on in there to get everything to work just right. So successful collisions result in reaction products breaking and or product formation, okay? So like I said, if we want to make sure we make sufficient amount of product, well, we increase the collisions. And one way is to increase the concentration because we need more collisions to make a product, okay? But the collisions have to be with enough energy to make that product. And we call that energy the activation energy. That is to activate the reactants to eventually make a product. If you don't have enough of that energy of activation, you're not going to make the product. Okay. And sometimes, we run reactions as chemists and nothing's happening. We let it run for hours, nothing's happening, analyze the solution, nothing's happening. So maybe sometimes we pick up the temperature. And maybe this time we get a product. Okay. But you got to be careful because sometimes the product is heat sensitive. So if you're at a high temperature, you make the product, but then the product being insensitive to temperature breaks down to make something else. And so you're really spending a lot of time playing with different variables to get to the product that you're trying to make. All right. And we talked at length about orientation. We're going to have the right orientation. Okay. We can increase the concentration to increase the rate of the reaction. That's what that bracket. Remember the bracket under pH chapter? We have brackets called concentration or molarity. Increase the molarity of the reactants. We get more products. We get more collisions. We get more products. Okay. Obviously, by increasing the temperature, we get the molecules to move faster. Molecules are not stationary; they are moving, and as we heat them, we get a more chance of becoming products. Also, too, if you have solids being in a solid form, if we don't do something to get them into a different state, maybe dissolve them in a liquid, solid reactions, though can occur, are not very efficient as far as making product. So you may have a solid that you maybe have to dissolve it in a solvent, put everything into molecules so they can react and form product. Okay. We can add a catalyst. A catalyst will help us get a reaction to occur. And what it does, it lowers this energy of activation that we talked about earlier. The energy of activation has the symbol E subscript A, denoted here, lower E subscript A. That means that the energy of activation. And by doing that, then this reaction doesn't require as much energy to get over the hump, so to speak. But it could be quite dangerous. Personally speaking, I once had a reaction that I had done numerous times and no problem. Put everything, put it into a container and just walked away from the hood and, let it run for a time period and come back and analyze the products. This time I put them together. I walked away from the hood and no sooner than I walked away, I had a big explosion. And anyway, shook up the lab a little bit. Glass all over the place, not too much of a problem. What had happened was this reaction that I had run numerous times, I had to wash the glassware a certain method because I did not want any trace metal. Well, I inadvertently forgot a step. And I had some trace amount of iron, specifically iron 3 in the container, and that catalyzed the reaction so quickly we had an explosion. And we have a lot of examples where reactions are very explosive. TNT, explosive, bomb material. Their reactions are so quick, so fast. They just boom. Okay. There are a lot of reactions that occur in your stomach that if it wasn't for catalysts in your stomach, name AKA enzymes, you would not be able to exist as we exist because those reactions in our stomach would take forever, years to do what it has to do without the catalyst. The catalysts are very important. Okay, so this energy of activation is the minimum amount of energy needed for a reaction to occur to turn reactants to products. Okay. Now we also have equilibrium reactions. We kind of introduced this to you a little bit when we saw the solubility of we talked about weak acids and weak bases. We explained that there was an equilibrium between the acid that was dissociated maybe only 5%, but we did make ions, but the bulk of it was still combined. Anyway, basically we have a double arrow. which states that the forward reaction is equals the same rate as the backward reaction, the left reaction. Okay, there's equal rates in this process. We tap into this quite a bit. A lot of reactions are equilibrium. We can do things to create more product. If C, for example, was a gas, okay, if it were gas, we could heat this. And this would be great. If C was a gas, we can heat this reaction vessel to drive the gas out, C, which causes the equilibrium to shift to the right. Because being an equilibrium reaction is striving to maintain that equilibrium, just like the pH is in your blood, trying to maintain that pH equilibrium. So sometimes we're lucky we know it's an equilibrium reaction. We can do things to the products to drive the reaction to the right. All right, well, we have what's called energy profiles. So let me explain a little bit about this before we go into that graph you see in the top right. Okay, so I'm going to kind of create my own graph here and see what color are we. So I can take a reaction, and like I said, I used to do reaction kinetics. So we followed reactions over a given time period and studied them. Okay, and did them in different temperatures, and we do all kinds of crazy things so we can get information. But at the end, we can create a graph in which the y-axis has energy units. It doesn't make a difference what specific units, but they're energy units. Okay. Now, if there is a way for us to look at a reaction and just take a snapshot at different time periods, this is what we call what's called the Ration Coordinate, but basically, really just time. If we were to put A and B together and then take a snapshot of that reaction, we can see what's happened at that given time. And then 10 seconds later, take a snapshot, do it again. So we collect data points and see what's going on as the reaction proceeds, okay? The result is this. We end up with a graph that maybe starts about maybe something, let me start about right here. It goes up and then maybe ends up right about here, okay? Now, the reactants, which I'm going to denote, all began at some energy level. Okay, so I got 10, 20, 30, 40 units of energy. So I got 10, 20, 30, 40, 50. It's a graph, okay? 60 energy units, 70, I'm going to go all the way up to 80 energy units, all right? So before the reaction proceeds, I have my reactants operate at some energy level, which in this case looks like 40 units of energy, 40 E, that's what I'm going to say, okay? Now, once the reaction is done and everything's down to where, done, process is done, our products, whatever they may be, occupy its stable state. And if it has its own energy level, and if we extrapolate all the way to the graph, we know, the dotted line, that energy state is 10 energy units, 10 E, okay? So you can see right away that our reactants start off at 40, but end up at 10. Now, one more area. If we take where the reaction started and we extrapolate across about right here, this distance from the top of the hill to where the reactant started off, that energy is what we call the energy of activation, because up on top of the hill, this is where the transition state is. That could be 80 units of energy, okay? So that difference of 80 minus 40 tells us that this energy of activation requires 40 energy units. That's how much energy this reaction is required to overcome that hill to become products. Okay, so that's the energy of activation. Now that distance between where the products were to where the products finally ended up, that's the change of what's called delta H. That's the energy of the reaction. And that is delta H is calculated by the energy of the products minus the energy of the reactants. So in this example, the energy of products we said was 10E, right? And the energy of the reactants was 40E. So you can see the delta, that's what delta means. The change of energy is a negative 30E. Negative. The important part is that negative value. What that negative value tells you is that this reaction is, remember way back when we were talking about exothermic reactions? Came back today, huh? Exothermic reactions. Those are reactions that give off heat. They get hot, okay? And so our value here will be a negative value. So the energy of the activation is the difference between the transition state and where the reactant started. The delta H is the difference of energy between where the products ended from where they started, okay? And so be familiar with where the reactants are, where the products end up, where you can define delta H or the reaction. Delta H is the reaction, the energy of the reaction, and where you can define the energy of activation for the reaction and the transition state. And I arbitrarily put numbers in there to demonstrate why things are negative. It gives you an exothermic reaction, or vice versa, that an exothermic reaction will end up with the energy of the reaction as a negative value, okay? We will learn that occasionally the product's energy level is above where they started, something like this. Well, in this scenario, you end up with a delta H with a positive value, okay? Because the products are at a higher energy level than the reactants. So the difference between products and minus gives you a positive reaction. Okay, so the transition state, that's what the graph in the top right means. I kind of broke it down for you and how that values, if you will, if you need to calculate, you can arbitrarily put numbers in there if numbers make more sense to you. Okay, let me clear this mess up here. So the transition state is on top of the hill. Delta H is the change of the heat energy. That's the change of the reaction energy. Okay. And that is the energy of the product minus the energy of the reactants. And if it were an endothermic reaction, remember we talked about this in the previous chapters, heat is a reactant. And what results in the system getting cold, it's an endothermic reaction. If heat is given off, then heat or energy is a product, and it's exothermic reaction. I also told you that if you go to the hardware, I got hardware store in my brain. You go to the pharmacy store and you get a cold pack. You can buy cold packs and hot packs. You get them, you smack them, they get cold or they get hot. If they get cold, it's because the reactants in that container are endothermic. You can use it out, put it on your sore muscles or so forth. If it gets hot, it's exothermic because heat is given off, okay? In that diagram, the energy profile kind of just gives you a description of what's going on. So in this reaction, it's asking you a question, is this an exothermic and what is the delta H? Well, you could do one or two things. One, you can remember that the energy of my products is much lower than the energy of my reactants. So if I subtract the two, I'm going to end up with a negative. Or I can put numbers on this axis here and do it mathematically to demonstrate to you that you end up with a negative delta H, which means that it's exothermic, okay? All right, a couple more slides and I'm going to be done. I got to hurry up here. Notice here in this example, the product energy level is much higher than where the reactants ended up. And so you can see if I do the mathematics, delta H here would be bigger number, call it, I don't know, call it 50 minus 10, you end up with a positive number. So this would be an endothermic reaction. Okay, be able to label where at least these 5 symbols or states, or I don't want to call, be able to label these 5 places on the profile where the reactants are, where the products are, where the transition state is, where the energy of activation is, and where is delta H. Okay, so looking at this, obviously we got a positive delta H because, again, from an energy perspective, the products are in a higher energy state than the reactants. Okay. And here are the 2 examples of exothermic and endothermic. Okay, notice again, to distinguish the 2 at a glance, you can see if I look here and I look here, okay, if I just arbitrarily say 10 energy units for my products, 10 E for my reactants, I don't know, call that 20. So delta H would be products minus energy. Okay, delta H would be 10 E minus 20, which is minus 10 E. Okay, minus. If I do it for the bottom one here, call this 10, maybe this one 30. All right, so delta H will be 30 E minus 10 E. I end up with positive 20 E. Okay, this is positive, this is negative, this would be exothermic, this would be endo. Okay, there's one way to do it. The other way, just to recognize that products energy level, final energy level, is much lower than my reactants for exothermic. For endothermic, products energy level is much higher than my reactants for endothermic. Okay. And then with respect to the catalyst, like we mentioned, the catalyst helps a reaction proceed much quicker. And it's simply because what it's doing is with the catalyst, the energy of activation for that reaction is lowered. So you can see here that the energy of activation is much lower with the catalyst. So that means that a reaction that may require little energy, little heat, can now maybe occur at room temperature with the catalyst, okay? Because that energy of activation has been dropped down. All right, so ladies and gentlemen, congratulations. In chapter 11, I told you it'd be quick, just in time too. I got 2 minutes to spare. Anyway, that